that I want to talk to you guys about is titration. Okay, and titration is a very specific lab technique that's used to determine the concentration or moles per liter of an unknown. And so here is here's kind of the setup, and some of you guys that have been in lab or watched some of the lab videos have seen this type of setup. We basically have a ring stand. So this is a pull on a heavy base. Okay. And this is a special kind of clamp to hold a burette. Now, a burette has these graduations that you can read, kind of like a graduated cylinder, except instead of dumping out of the top, instead we turn this stopcock, and when it's up, the solution up here drips out, okay? And it drips into the flask below. When it's horizontal, it doesn't drip. When it's vertical, it does drip. So in this burette, what I usually have is something I know. Well, someone wrote drip, drip. Are you guys going to sing that Encanto song to me? So known concentration of either a strong acid or a strong base. Oh my gosh, because you wrote drip, drip in there, I'm really like just mentally singing that Encanto song. So I'm trying to think about chemistry, but like singing that song. Okay, so up here we have a known concentration of a strong acid or a strong base, right? So that strong acid, when you add it to water, is going to completely dissociate to an H+, or the strong base will completely dissociate to the OH-. Now down here, this is called an Erlenmeyer flask. And in this flask down here, we can have a weak acid or base or a strong acid or base. And I'm going to write these backwards. So if you want to know something about the weak or strong acid or base, right, and this is our unknown down here, then we take and react the acid with it. If we want to figure out something about the acid or the concentration of the acid, then we drip the base into it. Okay, this molecule here is called phenolphthalein. And remember, every end and bend is a carbon. So this has a carbon ring, a couple of carbon rings, a big carbon here, some oxygens, and an OH. That's called an alcohol. And phenolphthalein is an indicator. And when you have H+ around, it's clear or colorless. And when you have OH- around, it's pink. So if down here you have H+, you add phenolphthalein, this whole thing is going to be clear. Okay, so how this reaction works, right? We have a base, like we'll just say a base of a known concentration or of a known concentration. And so remember, we want to use a strong base, and that strong base has an OH-. Okay, we're going to drip this down into an acid of an unknown concentration, right? So here's our unknown, what we're trying to find. And an acid has H+ that reacts, okay? And in the bottom in this flask, we also have that indicator, that phenolphthalein indicator. So when we have this reaction, we have our OH- at the top is going to react with our H+ at the bottom. And I put an equal sign, we're going to form 0. No, we're going to form water, right? So H2O. So remember, because of phenolphthalein, if there's acid around or H+, it's clear. And if it's OH-, it's pink. Okay, so this flask right here represents this one up here. So because it's clear, that means there's H+ around. Now, when I drip that first little drop, what happens is in that drop, in that moment, there's OH around. So the indicator turns pink. So right here, that means there's OH right in that little spot. Now I keep dripping this OH in here until I reach what's called an equivalence point. Okay, the equivalence point means that the number of moles of OH minus equal the number of moles of H plus in that flask. Okay, and this pink color, you want to just be the faintest light pink color that you'll ever see. Okay, now if you keep dripping OH minus in, what happens is you over titrate, is what it's called. And so if you have a bright pink solution, then you have too much base. Okay, because now all you have is OH around. So the goal of the titration is to get to this equivalence point, or this very, very light pink color, so that you know that the moles of OH equal the moles of H plus. Okay, so we can look at that with this example. So how many milliliters of 0.200 molar NaOH is needed? Right? So automatically I think, okay, how many milliliters? And then I have a base, NaOH, and I have a molarity. So how many milliliters is needed to titrate 35.00 milliliters of 0.10 molar HBr to the equivalence point? And remember that equivalence point is when H plus equals OH minus, right? The number of moles of H plus equals the number of moles of OH minus. And tell me, say, Dr. Fuller, always put your units. So moles of H plus, moles of OH minus. Okay. Now, the very first thing when I'm doing these problems is I want to visualize my titration, so how it's set up, and I also want to write my balanced chemical equation, right? So what reaction is going on? So I'm taking sodium hydroxide and I'm titrating, or I'm adding it, right? So I take sodium hydroxide and I'm adding it to HBr. Okay, you guys recognize these are both strong acids, or both strong, right? So this is a strong base, so it's going to dissolve, and this is a strong acid. When I react a strong acid and strong base together, I form water and sodium bromide, right? I form that salt. So this is the reaction that's actually happening. Okay, so I have my reaction. The next thing is it balanced? And so on this side, I have one sodium, one oxygen, two hydrogens, and one bromide. Okay, so my reaction's balanced. So I know my reaction, I know it's balanced. Then I think about the actual setup, right? So let's draw this burette. And I draw my Erlenmeyer flask. And you guys can see why I wasn't an art major, right? Someone asked me about the hydrogens. So I have one hydrogen here, one hydrogen there, and then two right there. So my hydrogens are balanced. Okay, so this question says, how many milliliters of 0.2 molar sodium hydroxide is needed to titrate? So titrate means it's going to be added. So I want to know how many milliliters of the sodium hydroxide solution. Okay. And I know that solution is 0.200 molar. So how many milliliters of that solution is needed to reach the equivalent point? And down here I have 35 milliliters of 0.140 molar HBr. Okay, so if you look at this, I want to know this information. So how many milliliters of sodium hydroxide solution? And what I start with is what's in my hand. And what's in my hand is 35 milliliters of HBr solution. Right? So I wrote my reaction. Step 2 is I pictured what was happening. And step 3, I started outlining my plan, right? What I have or what I can hold, what I know the most information about, to what I'm looking for. Okay, so I'm going to go to the next slide. I have my question here at the top. I have my balanced chemical equation written afterwards, and I've started my plan, right? I start with my milliliters of HBr solution and my milliliters of sodium hydroxide solution. The question asks how much of the sodium hydroxide is needed to reach the equivalence point. That equivalence point is based on this balanced chemical equation, right? So I know that for every 1 mole of HBr, then I have 1 mole of sodium hydroxide. Okay, and so we're going to use that conversion in this process, right? Because I'm changing labels. And when I go through that process, it's going to automatically be the equivalence point. Okay. Now, some of the information I'm given is, and I should have written that on one line, is the concentration. Okay. And so I have 35 milliliters of this 0.140 molar HBr solution. Okay. And because I have that, let's just write this number down here because I don't like it when my numbers are separated from my units and labels. To use molarity, I need to get to liters. Okay, so I know for milliliters, I'm going to find liters of HBr. Okay, and I know that 1,000 milliliters equals 1 liter. So notice anytime you have milliliters, automatically kind of think, oh, I need to change to liters. Okay, my next step of this is I'm going to go from liters to moles. And when I do this, guys, I didn't write this down, but I have milliliters of HBr solution goes to liters of HBr solution. Right? Next, I'm going to use my molarity. And when I use molarity, I'm going from liters of HBr solution to moles of HBr. Okay. Now here's where, since I have moles of HBr, I can actually go up. These equations, these balanced chemical equations, has to do with moles, right? So because I have moles of HBr, I can actually convert from moles of HBr to moles of sodium hydroxide. So 1 mole of HBr equals 1 mole of sodium hydroxide. And I use the coefficients to do that, right? This is where my equivalence point is. That's where this is taken into consideration. The equivalence point is when I react my moles of HBr with my moles of sodium hydroxide. Okay, and then I can follow kind of the steps in reverse. I have moles of sodium hydroxide. From moles of sodium hydroxide, I'm going to go to liters of sodium hydroxide solution. And I'm going to use molarity to do that. And then liters of sodium hydroxide to moles of, or milliliters of sodium hydroxide using the conversion. Okay, so this step right here, I go from moles of HBr, I use the coefficients to switch to moles of sodium hydroxide, and then I go backwards to go to liters of sodium hydroxide solution. Okay, so there was a question with this, can I use M1V1 equals M2V2? Titrations and dilutions are very different. Mathematically, like if I'm going to be honest, mathematically it will work because it's a 1-to-1 ratio. But you should really only use the M1V1 equals M2V2 formula when you're doing dilutions that have the same unit and label. Okay, so mathematically it will work out, but that's only because of the 1-to-1 relationship. And so technically it's not correct to use M1V1 for titrations. You can only use M1V1 equals M2V2 for dilutions. Okay, so let's go to the solution, right? So we have our question at the top. I have my balanced chemical equation here, and then I've typed up the plan because you guys know my handwriting can get kind of crazy. So my very first thing, I write down my 35 milliliters of HBr solution. And here I'm converting from milliliters to liters. So I start with my HBr solution. Because I have milliliters at the top, I'm going to use milliliters at the bottom in this very first step. So very first step, milliliters of HBr solution from the top cancels with milliliters of HBr solution that's on the bottom. I'm left with liters of HBr solution right here. Okay. For my next step, I use molarity, and this is the molarity of the HBr, right? So I come up here, molarity of HBr, that is 0.140 moles over 1 liter, okay? Because I have liters up here, I'm gonna put liters at the bottom, and pay attention to those labels. Liters here at the top cancel with liters at the bottom, HBr cancels with HBr, solution cancels with solution, and I'm left with moles of HBr. Okay, I have my equal sign, so I multiply 35, I multiply 1, I multiply 0.140, I divide by 1,000, I divide by 1, and the answer I get, the answer I get is 0.004900 moles of bromide right here. Okay, now notice what I did is here I have 1, 2, 3, 4 significant figures. Here, I don't worry about significant figures. Here I have 1, 2, 3 significant figures. So when I write my answer, I write 1, 2, 3 significant figures, but I'm carrying those extra digits, right? I want to carry as many digits possible throughout this problem. So I'm at moles of HBr. I'm going to do my step number 3. Okay. Step number 3 has the coefficients from the balanced equation. So I know 1 mole of HBr equals 1 mole of sodium hydroxide. So my moles of HBr go on the bottom to cancel with the moles of HBr at the top. So there's my step number 3. Next, step number 4. So with step number 4, I'm going from moles of sodium hydroxide to liters of sodium hydroxide solution. And the molarity I have up here is 0.200 molar sodium hydroxide. So that means for every 1 liter of sodium hydroxide solution, whoops, that says NaOH, I have 1 liter of sodium hydroxide solution, right? So, oh, I went forward. So up here, because I have moles of sodium hydroxide at the top, I have to put moles of sodium hydroxide on the bottom, right? Anytime you have a ratio, you can write 1 at the top and 1 at the bottom. So my moles at the top cancel with my moles at the bottom, sodium hydroxide cancels with sodium hydroxide, and I'm left with liters of solution. Okay, again, I'm going to multiply the top numbers, divide that by 0.2, and I get a number with, again, I'm going to use 1, 2, 3 significant figures and put the other little just to keep track. My last step, step number 5, is to convert from liters to milliliters. Because I have liters at the top, I'm going to take and put those liters at the bottom. And my units and labels stay, or my units change, my labels stay the same when I'm using this conversion. So liters at the top cancel with liters at the bottom, sodium hydroxide cancels with sodium hydroxide, solution cancels with solution. And I'm left with milliliters of sodium hydroxide solution, which is what my problem asked me for. I take and move my decimal place over 3, right? I multiply by 1,000 and I get 24.5 milliliters of sodium hydroxide solution.